the chapter with at least 2 out of the 3 significantly large sections. Today's section is on the shorter side. It's only 35 slides long. The one after that, 10.2, is 66 slides long. And we will start that one probably today. It'll depend. If not, we'll be starting it on Wednesday. So I doubt we will get to finish it by Wednesday. I'm not really sure. We'll just have to see how things go. But this is the section that I pretty much told you guys we cannot we can't afford to have too many missed classes. Come on. Thank you. Okay, so the next topic we're going to look into is polar coordinates and polar vectors. Polar coordinates, not super hard. They will have a little bit of a different feel for you if you haven't worked with them before. So this is what you want to recall, basically. Obviously, the system you're used to working in is the rectangular coordinate system, where we have our x-axis and our y-axis, and you're typically plotting x and y points. And obviously, we can do our different functions as well. But typically, for the sake of argument, we're plotting our x and y points. For polar coordinates, the origin is in the center still, but then we have what are called poles and polar axes. You can see a little bit of the diagram there. That's just kind of reinstating a little bit of how similar it is to the rectangular coordinate system, but it does actually work a little bit differently. Instead of having x and y, we're going to have r and theta, so essentially radius and theta. And if I go too fast, please just watch the video or tell me to go back. This is your class, so if you need me to go back, I'll definitely go back. So here you can see a little bit more in depth of polar coordinates. So a point P in a polar coordinate system is represented by an ordered pair of numbers. Like I said, radius, comma, theta. So r is the distance of a point from the pole, and theta is the angle either in degrees or radians. I would suggest if you're going to draw diagrams, you can have more than one polar coordinate on the diagram, but I would have one for degrees and I would have one for radians. Okay, I wouldn't combine those two. So we call the ordered pair r comma theta the polar coordinates of a point. So essentially, you're kind of basically still plotting x and y points, except your y is more of it angle based, if that's easier for you to think of it that way. And as I said, the origin is now going to be referred to as the pole. So we're going to do a couple of examples. And I typically would do them over in the whiteboard, but I have a feeling my drawings are going to be terrible. So we're going to try to do it on the slide. That way you guys can just stay within the PowerPoint. Okay, so if we want to think about plotting the points, the polar coordinates, 3, 5 pi over 3. So 5 pi over 3, where's that going to be? Where do we want to kind of have our angle at? So I'll try to make a.
But now we want it in the fourth quadrant.
Yes. Okay, I'm going to try very hard to draw this as neatly as possible. So it's not really, it's kind of like that. All right. And then you'll see in the next slide, it's kind of nice how they do it. They mark it out, and obviously their marks are a lot nicer. So we go from 0 to your angle, and then we counted down 3. So that would be the point 3, 5 pi over 3. Okay.
The first digit is like vertical, like in the y in the rectangular coordinate system.
Yes, kind of. So that's the best way I can think about it in terms of like trying to kind of get your mind around this initially. It is R, but for what we're used to working with, if you can see it as like quote unquote the Y, then you can think of it that way. But we will show later on there is a way to go from polar coordinates to rectangular coordinates. So they're not equivalent. It's just if your brain kind of helps you see it that way a little bit more, then you can use that to kind of help you. But notice that this 3 is positive, whereas if you were to go with the rectangular Y, you would have a -3 there. So there is a difference. So okay, so the next one we're looking at is 2 negative pi over 4. So again, we're going to end up in the fourth quadrant. But this time, instead of going all the way around, we're actually going to start from, apparently I have Halloween on the brain. I just used orange and black in both of our examples. Okay, so there's our pole. It starts at the origin. And so our theta here is negative pi over 4. Okay, and then we're just counting 2 on that line. So just like that. And again, it's r comma theta. Okay. Now, probably one of the more confusing examples is going to be the next one, because you're looking at just 3 and 0, which means it literally looks the most like a coordinate point. but that's because 0 is an acceptable theta. Okay. And then the last one is -2 comma -pi/4. And for this one, when we get down to it, they decided to show us the whole line, and I'm not really sure why they chose to do it that way, but we will emulate it the best we can. Okay, so that's probably not drawn perfectly, so I do apologize. Yeah, because that is not to scale. So what they did is they drew, and I don't know why, again, I'm not entirely sure why they took this approach, but they drew pi/4, and then they said, well, if that's pi/4, then this down here, 1, 2, is -2 pi/4. Okay. All right, questions on that? I am gonna go to the next slide so you guys can see it a little bit nicer, but I will save this in case you guys want to, for whatever reason, would rather have my copy. Although, if I were you, I would go with the nicer ones. Who knows? Maybe you guys would be interested in having the Halloween version. Okay. All right. So the next thing we're going to look at is finding several polar coordinates of a single point. So before we even get to it, why do you think that's a possibility? Why do you think it's possible to have the same polar coordinate but have it represent multiple polar points? What do we know about angles at this point? What do you guys think?
Like don't angles repeat over time. I mean, repeatedly.
Right, they repeat, right? So you're looking at every 2 pi or however many you want to go. So we have to have a way to kind of account for that. All right, so just because we draw the figure in A does not mean that the figure in B or the figure in C are the only way to get to that, okay? So you can be sitting there and going around in circles literally all day, and you're going to come across it many times, okay? Okay. All right. Okay, so if we look at figure D, why is this figure important? What's it showing you?
I think that if it's either the radius is negative, positive, it's still the same. It's still the same.
Yeah, so it's still the same ray. If you want to have a negative radius, you have to find the corresponding angle, okay? So if you are given the positive radius and then that corresponding angle, if you want to find the negative radius, then you have to just figure out the comparable angle, okay? And you guys practice that, what, in chapter 8, I think? So it's just coming together a little bit now. All right, so example 3 says finding the polar coordinates of a given point. Plot the point P with the polar coordinates 2 pi over 3 and find the polar coordinates r theta of the same point for which, and so for solution A, they want r to be greater than 0 and for theta to fall between 2 pi and 4 pi. For solution B, they want r to be less than 0, and then for theta to fall between 0 and 2 pi. And then for solution C, they're looking for r greater than 0, but then theta between negative 2 pi and 0. So before we go through anything, you can see the given polar coordinate is drawn for you there. So that before you can go through and figure out your conditions, A, B, and C, you have to start with the initial figure, okay? So if we were to consider condition A, which is r greater than 0, and that the angle is falling between 2 pi up to but not including 4 pi, what do you think we can do? And then additionally to that, do you guys think you're actually going to be drawing a different diagram each time? Or do you think your representation of the angle is just going to change each time?
I think it's just a representation that's gonna change.
Very good. Okay, so let's take a look at A. So to get to A, all you had to do was add 2 pi. Okay, your R is staying unchanged. Okay, and you can tell that that's going to fit the condition. Okay. All right. So for B, we're going to add half a revolution to the angle. So we're adding pi. And then we have to replace the 2 for the radius, for the r. We have to replace it with the negative. And And why do you think we had to do that? The condition in B told us that R had to be what?
-2.
Right, it told you it had to be less than 0. And now we're not going to make it a new coordinate each time. We can't just pick the R. We have to make it related to what we're given. So that's why we're going with -2. And again, if I go too fast, either tell me to back it up or I will be putting the recordings up today. So, okay, so for condition C, we had a positive radius again, but then our angle is changing once again. So now instead of adding 2 pi, we're subtracting 2 pi. Okay. But you can see the actual diagram didn't change. It's just how you're drawing the angle. Okay. So the summary here is just basically telling you that you can have either R and then theta plus 2 pi k, or R negative and then theta plus pi plus 2 pi k. K being any integer and the coordinates of the pole are 0 theta, where theta can be any angle. Okay. That is it in terms of graphing polar coordinates. Now the next thing we're going to look at is converting from polar coordinates to rectangular coordinates. And that's why we said you can't just really say that it's R, that Y is just R. So in order to convert from polar coordinates to rectangular coordinates, or to go from R comma theta to X comma Y, we want to look at X equal to R cosine theta and Y equal to R sine theta. Okay, so those are your two formulas that you'll want to work on using for this section. So if we look at the example, we're going to want to find the rectangular coordinates of the points with the following polar coordinate 2 and pi 4/4. So if we use the formulas, okay, what are we going to find? You guys can do it. I'll write it out, but you guys can definitely figure it out. So X is going to equal R, which is 2, cosine pi/4, and Y is going to equal R, which is 2, sine theta, which is pi/4. So what do you guys get? What's your X comma Y going to be?
I got both of them at the square root of 2.
Okay, so that is what it would look like, but we will go ahead and clear it and I will show it in the slides. Okay. So they'll both be positive because they're both going to take a quadrant 1. And then, yes, square root of 2 comma square root of 2. Okay. So now what happens when we consider the opposite? When we go from regular coordinates, rectangular coordinates, sorry, to polar coordinates. What do you think we're going to have to do? Okay, so let's work through this example. We're going to convert from rectangular coordinates to polar coordinates with a point on a coordinate axis. So the point they want us to look at is 0, 2. So we plot the point in the rectangular coordinate system, and the point lies on the y-axis. Okay. Well, if it's sitting on the y-axis, and we typically start from x, then of course it makes sense for our angle to be pi over 2, right? Right, so then it says the point 0, 2 lies on the y-axis, a distance of 2 units from the origin or the pole, so then r has to be 2. A ray with the vertex at the pole through 0, 2 forms an angle of theta equals pi over 2 with the polar axis. So the polar coordinates for this point can be given by 2 comma pi over 2, but we can have other representations as well. We can have -2, negative pi over 2, and we can also have 2 comma 5 pi over 2. So again, your representations are important, okay? So take this down. These are points that lie on either the x-axis or the y-axis. So the figures show polar coordinates of points that lie on either of the axes, and each illustrate an a greater than 0. Okay, so you're looking at positive r values. Why they wouldn't just use O? I guess because a is representing y, not r. So these, if you can kind of memorize these for diagrams, then you can kind of place them in as you get other options. Okay. All right, so for example 6, we're looking at converting from a rectangular coordinate to a polar coordinate. And now we're looking at a point that's actually in one of the quadrants. So the point they give us is 2, -2. Okay, so if we draw that, you can see that it's going to land in the quadrant 4. The question is, can you guys figure out, can you at least figure out what r would be? How do you think you would figure out r? Well, why don't we take a second and remember the equation for a circle, right? So a circle is r squared equals x squared plus y squared. So if you use that, then r is just going to equal the square root of x squared plus y squared. Okay. So you have to find r first. Well, I guess really the true first step is the diagram. And the diagram is going to help you probably because of signs. All right. And then what function is going to help you find theta?
One of the conversions from polar to rectangular help you to find theta?
Um, you can try it. It can be an experiment for you. The recommendation is going to be using tangent theta because you're looking at an x and a y. Okay. All right. All right. So let's see if you, those of you that did it by hand, let's see if you got it right. So r is going to be the square root of 8 or 2 square root of 2. And then if we use the tangent of theta, that would just be what the inverse tangent of -1. Okay, so we get negative pi over 4. Okay. So you're looking at 2 square root of 2 and then comma negative pi over 4, or there are many other possibilities as well. So let me just tell you the caveat here. If you give me an equivalent answer on your exam for chapter 10, I will give you the points. However, if you could try to keep it within a certain framing and not just give me a representation because it's out in left field, I would prefer it. But obviously, I will give you credit if the answer is correct. Okay, so this is just walking through another example. They gave us -2, which lies in the third quadrant. So again, the first step, they drew it. Second step is going to be to find your R value. Well, -2 squared and -2 squared, that gives you 4 and 4, which is the square root of 8 again. So R is going to be 2 square root of 2. Okay, so there's that. All right. So now what we have to try and think about is our tangent. So we're kind of stuck in the same. Well, that's interesting. Oh, there they go. Now they're going to work it out. Okay, so they worked it out pretty similarly to the last problem, but we have to realize that we're in quadrant 3. So to go from quadrant 1 to quadrant 3, we have to add pi. Okay. Now, if you were back here and you said, oh, well, that's pretty similar to what I was just working with, 2 square root of 2. So then I have to be looking at something related to pi over 4. If you remember that you can do -2 over 2 and get yourself pi over 4, you can do that as well. Perfectly legal. Okay. Any questions on any of those examples? Okay, we're not done yet. Go ahead and write your formulas out, especially if you're taking notes by hand. So it gives you the steps for converting from rectangular to polar. Always plot the point first. Note that the quadrant the point lies in, or the coordinate axes the point lies on. Okay. If x equals 0 or y equals 0, use your illustration to find r. If x and y are not equal to 0, then you have to use r equal to the square root of x squared plus y squared. For step 3, you want to find your theta. Okay. And then you also want to pay attention to which quadrant you're in. Note for quadrants 2 and 3, we have to add pi to our tangent. Okay. All right. I'm going to wrap this PowerPoint up. Object 4 is transforming equations between polar and rectangular forms. So if we want to transform the equation r equals 4 cosine theta from polar coordinates to rectangular coordinates and identify the graph. Okay. So you literally just start manipulating. Why is it important to go from r to r squared? Because you're going from polar to rectangular, right? When we do the equation of a circle, r squared equals x squared plus y squared, that's in a rectangular coordinate system. Okay, so if we can get to r squared, then we can easily get to the equation of a circle. Okay. All right, so if we write it, if we write it in standard form, then we see that the circle has a center at 2, 0, which means we have a radius of 2. Well, that we have a radius of 2 as well. Okay, so that's going from polar to rectangular. What do you think our last example is going to be? We're going to do the opposite now. We're going to go from rectangular to polar when you're ready. Okay. All right, so we want to transform the equation 4xy equals 9 from rectangular to polar. So what's the first thing you want to do? What do you know about x and y?
The x would be the the r cosine of theta, and then y was the r sine of theta.
Yep, so we're going to take those and we're just going to place them into the function. And then when we rewrite it, it will look like the following. And then the only thing we have to do now is kind of simplify it. Yeah, I guess simplify it. So we're going to pull out 2r squared. And then you can see that it's 2 sine theta cosine theta, so it can be rewritten as sine 2 theta. So that is it for section 10.1. Section 10.2 is significantly longer. Okay. So we're going to look at polar equations and graphs. All right, we're going to identify and graph polar equations by converting them to rectangular equations. we'll graph polar equations using probably Desmos, because that's what I can easily show you. And then we will test polar equations for symmetry and graph polar equations by plotting points. Okay. All right. So what's really cool is if you're super nerdy like me, you can actually get, I'm pretty sure you can actually get polar grids. You can get like a notebook of them, but honestly, you don't have to. You can just draw it without it. You can also print out polar grids. So it's kind of up to you. It's also up to, what degree are you going for, that kind of stuff. If you think you'll be in a lot of engineering classes, physics, higher math, getting one notebook of polar grids might work out for you. I wouldn't get, obviously, a slew of them unless you like writing in circles. But yeah, I mean, I always write on graph paper all the time. But yeah, I would recommend getting at least one polar grid notebook, like off of Amazon or something, if you're going to do a lot of physics and engineering. And I don't think you would need it for chemistry, but polar grids, definitely cool. All right, here's your definition one. An equation whose variables are polar coordinates is called a polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. Okay, pretty standard. So we're going to dive into objective one. We want to identify and graph the equation r equals 3. Okay, so the first thing you want to do is convert it to a rectangular equation. Well, as we've said before, r, if we get it to r squared, it becomes rectangular. So if we are squaring the left side, we have to square the right side. So you have a circle with a radius of 3 and the center at the pole. So the center is at 0, 0. Right? And you can see it drawn on the right. Okay. Any questions on graphing something like that? Okay. All right, so the next one we're going to look at is, it says identify and graph the equation theta equals 3 pi over 4. What can we replace theta with that will help us get to a rectangular equation? What do you think? What did we use before? What trig tool did we use before to get theta?
Kind of tangent.
Yeah, we did tangent. So we're going to replace tangent theta. And if we're taking the tangent of theta, we have to take the tangent of 3 pi over 4. Well, we know from our definitions that tangent of theta is equal to y over x. Okay. Well, tangent of 3 pi over 4 is just -1. So then y equals -x. Okay. So then I'll show you the rest of it. All right, so that just shows you that we did it correctly. And then here you can see your figure. All right. And it's the entire line actually. If you wanted to get potentially some bonus points on your exam for chapter 10, if you get either printouts of polar grids, or if you end up, buying some polar grids, I will definitely give you bonus points if you end up turning your work in on polar grids, because I think that would be cool. All right, the next example is a horizontal line. So we're looking at r sine theta equals 3. Well, we know that r sine theta equals y, so y equals 3. Okay, that one's pretty easy. If we were to do r cosine theta equals 4, then you would have x equals 4, and that would be a vertical line. Okay. Objective 2. We want to graph polar equations using a utility. So here's the first thing. When it comes to graphing, step 1, we're going to solve the equation for r in terms of theta, which is not new. You always solve it for y in terms of x. So r in terms of theta. Step 2, select the viewing window in polar mode. Okay. And I imagine these steps are for like your TI-83, TI-84, the pluses, though I think that's these ones. If you have the monstrosity that I have, where is it? The HP. Let me just bring this guy out. So if you have him, the HP graphing prime, probably not going to be nearly as nice as steps. I think I've told you guys before that I'm definitely going to have to spend some time over winter break YouTubing how to use my calculator. Very annoying. Okay, so you want to make sure that you check your X mins, your X max, your X scale. The viewing window in the polar mode requires setting minimum and maximum values for theta and an incremental setting for theta step. Finally, a square screen and radian measure should be used. All right. Step 3, enter the expression involving theta that you found in step 1, and then press graph. I just told you all of that. If you choose to use your regular graphing calculator, you may do so. However, I would highly suggest that you use either Desmos or some other free online graphing tool instead of messing up your calculator. Because more likely than not, in between all, like if you're done using it for polar, you will probably have to reset the calculator to get it to work right. Totally your decision. I'm not going to tell you that you can't use your graphing calculator, but I would definitely recommend taking the approach of using an online calculator. All right, so let's use a graphing utility to graph the equation r sine theta equals 1. Well, we already know what that should look like, right? Because that's just equal y equals 1. But let's do it the way they want us to do it. So r equals 1 over sine theta. So here's your step 2. Okay, so they put everything in radians: 0, -8, -5, 2 pi, 8, 5, pi over 24, 1, and 1. The theta steps determines the number of points the graphing utility plots. For example, if theta step is pi over 24, then the graphing utility evaluates R at 0, pi over 24, 2 pi over 24, 3 pi over 24 until it reaches the max of 2 pi. The smaller theta step is, the more points the graphing utility plots. So you want to experiment with different values to see what the graph, how the graph is affected. Again, you can do this, but I would suggest using a different tool. All right, enter the expression 1 over sine theta after the prompt R equals, and graph, and then graph. So let's see if we would get the same thing if we go into Desmos. So give me 1 second. Oh, I actually think I had a Desmos calculator open. So let me share that screen. Okay, so you can ignore what's on here for right now. Let's add a new one. R equals 1 over sine theta. And what was our, I guess we went between 0 and 2 pi. Okay. All right, so there you go. Same point, same line. No real points showing though. That's sad. All right. Okay. So again, completely your choice, but I would definitely recommend using Desmos over messing up your calculator. You can probably also Google just free polar graphing calculator or something like that, and I'm sure it'll come up. Desmos might actually be what comes up. Okay, so R cosine theta equals -2. Well, that's just x equals -2. All right, so you're going to have a vertical line at x equals -2. All right. Again, you guys can choose whichever way you prefer to do that. All right, let's look at the theorem. And what I do like up here is that they did show you that you can draw it by hand. Oops. So on the left is drawn by hand, and on the right is their graphing tool. All right, so go ahead and write down theorem 1. If we let A be a non-zero real number, then the graph of the equation R sine theta equals A is a horizontal line. It lies A units above the pole if A is greater than 0, and it lies the absolute value of A units below the pole if A is less than 0. The graph of the equation R cosine theta equals A is a vertical line. It lies to the right if it's positive. It'll lie absolute value of A units to the left if it is negative. Okay. So if we want to identify and graph the equation r equals 4 sine theta, what are we going to do? What's our first step to go from polar to rectangular? What do we have to get to first?
To either X or Y.
Right, we have to make it get into x or y, so we want to get to r squared first, right? So we're going to multiply both sides by r squared. So then we'll replace r squared with x squared plus y squared, and then we know that r cosine theta is x. So we end up having r squared plus or x squared plus y squared equals 2x, and then we're just going to solve.
Wouldn't it be sine Y?
Yes, I think I was looking at the next example. Sorry. Good call. All right, so again, you're going to work it down. You'll end up with x squared plus the quantity y minus 2 equals 4. I think there should be a squared there, right? Do you agree? They messed that up. There should just definitely be a square there. Okay. All right, so we can draw this either by hand or on the graphing tool, whichever way you would like. All right, it's a circle. The center is at 0, 2, and the radius is 2. So they use the polar grid, and they also use the graphing calculator. Now you can graph a circle, I believe not in polar, you just have to solve it for y first. Again, totally up to you what approach you would like to take. I would just use an online calculator. Okay. All right, the next one deals with cosine theta. So pretty similar problem. Okay. So they just multiply both sides by r. They replaced cosine theta with x. They went through and solved it. Here they remembered their little squared. It's another circle, either by hand or on the calculator. Any questions on those examples? Okay. Give you guys a few minutes if you're writing things by hand to write down theorem 2. So if we let a be a positive real number, then we have the following conditions basically. So r equals 2a sine theta, your radius is going to be a, the center is going to be at 0, comma a. If you have r equals negative 2a sine theta, then your radius is a, and then your center is at negative a. If you have r equals 2a cosine theta, then you have a radius of a, and then your center is at a, comma 0. And then likewise, a negative 2a cosine theta, you would have a radius of a and a center at negative a, comma 0. Each circle passes through the origin or the pole. All right. Any questions on the first two objectives? All right, then we're going to keep going. Objective 3 is test polar equations for symmetry. So we have points symmetric with respect to the polar axis, points symmetric with respect to the line theta equals pi over 2, and points symmetric with respect to the pole. Okay. So you're looking at 3 possible lines of symmetry. I'll say lines, air quoted. Whereas with our rectangular coordinate system, you can have an axis around, well, I guess there's also 3 there too. You can have a line of symmetry with the x-axis, symmetry with the y-axis, or you could have symmetry with the origin. But you can also have symmetry with other lines too, pretty sure. Right? So there is your theorem in written word. To test for symmetry, symmetry with respect to the polar axis or the x-axis. In a polar equation, replace theta by negative theta. If an equivalent equation results, then the graph is symmetric with respect to the polar axis. Why does that sound so similar? Isn't that basically how we find symmetry with the x-axis? Okay, it's basically got a little twist, but that's it. All right, in a polar equation, replace theta by pi minus theta, and if we get an equivalent equation resulting, the graph is symmetric with respect to the line theta equals pi over 2. All right. And then symmetry with respect to the pole or the origin. In a polar equation, replace r by negative r or theta by theta plus pi. If an equivalent equation results, the graph is symmetric with respect to the pole. Okay. There are not any examples for this section. And last, so we only have about 14 minutes left. So do you keep going, or do you want to pick up with objective 4 on Wednesday? Shout out what you want to do. All right, let's just pick up with objective 4 on Wednesday.